I'm Hawra Bahzad.
I'm Rantaj Singh.
I'm Jack Kerr.
I'm Walker Lewis.
I'm Tevin Broadhead.
And I'm Itay Ozer, and we're Team 21054, ground-based optical target tracker, with our sponsor being Raytheon Technology, Jim Backerich, and our mentor being Sharon O'Neill.
Our project goal is to develop an easily transportable real-time optical tracking system of suspicious vehicles at domestic critical infrastructure sites. The ground-based optical target tracking, also known as GOT. This system shall allow a user to choose a vehicle that the system can lock onto and follow through a cluttered background. The system shall be able to store each tracking event. GOT is an autonomous image processing tracking system that will track a full-size vehicle moving at approximately 28 km per hour at distances ranging from 50 to 300 meters orthogonal to the tracking system. In order to successfully design a robust working product while meeting deadlines and budget constraints, we had to prioritize working on specific subsystems first. We did that by considering the risks, cost, and possible lead time that come with each subsystem, as well as the dependability of the rest of the project on each subsystem.
Our product is constructed of 4 main subsystems. The first is the optical subsystem. This included the lens, detector, and laser. Second was the software subsystem, which included a laptop, target tracking algorithm, image processing algorithm, video storage, and user interface. Third was a motion control and electrical subsystem. This included a motion control algorithm and a portable battery. Finally, for the fourth was mechanical subsystem, which included the pan system, motion control hardware, stepper motor, and a tripod. Our team followed the agile methodology where we worked in 3 iterations. The first iteration focused on the optical subsystem because it was the centerpiece of the system, as the other subsystems were dependent on its performance. The second iteration focused on the design and fabrication of the pan-tilt design, as well as writing the target tracking algorithm. The last iteration focused on motion control and the overall system integration.
Because one of our team goals was to design an extremely robust system, we decided to create quite rigid camera requirements. As you can see here, we set requirements for resolution, field of view, distortion, and frames per second. Resolution defines how well the camera can differentiate objects. Since we needed the camera to depict a vehicle from 50 meters to 300 meters, we decided this parameter would be crucial for our success. We decided on an 80-degree field of view as we felt that this provided us with a large enough area for a tracking sequence. With a wide-angle field of view, distortion aberrations can play a huge role. Distortion is when we have a changing magnification across our field of view. In a machine vision project like ours, it is crucial to minimize this in order to have a synonymous relationship between pixel and world coordinates. Lastly, we held our frames per second to a high standard as all of our tracking algorithms will be dependent on the constant feed of image data. Once we finalized our imaging parameters such as resolution and focal lengths, we ran a trade study on our better options to determine the best camera for our system. Looking here, you can see how we weighted our factors. Cost and lead time were quite important. Parameters like SDK and connection type were considered because those two have abilities to simplify our integration and speed up our data throughput. We decided on camera 3 in this trade study as this camera satisfies our requirements as it had a 5 megapixel resolution, a low distortion, high frames per second, and was reasonably priced. So moving on over to the laser, for this system we procured a Class 3B green eye-safe laser, and we also got laser safety goggles as well.
Our project was to include a pan system capable of moving a laser to continuously designate the selected target. The pan system was crucial to the overall design of the project because it connected all the components in the system. The team modeled a simple design that could be easily fabricated due to lab space and COVID restrictions. The system was fabricated from 6061 aluminum due to its high strengths and durability.
For the motion of the laser, the system included a closed-loop stepper motor. Some important considerations in the selection of our motor were the torque, step size, microsteps, and the ease of integration into our system. Through our trade studies, the team selected the Trinamics motor. The motor is equipped with a microcontroller and encoder, allowing the motor to report its exact position during movements, adding more precision to each movement. Trinamic offered a simple GUI for the motor and pre-coded commands to easily change the access parameters such as velocity, acceleration, and deceleration, which proved valuable in the final testing and integration of the system. For more precise movements, a 1:3 gear ratio was incorporated, reducing our degrees turned per microstep. To easily integrate with the target tracking algorithm, the team decided to write the motion control algorithm in Python. After research, the team downloaded the PyTrinamic repo, which integrated the Python commands into commands recognizable by the motor. Because the motor has a 360-degree rotation, access parameters were set to align with the camera's field of view. The best way to integrate the target tracking and motion control algorithms was by calculating the percentage of the field of view that the target is located. Once the field of views were aligned, simple move to commands could be sent by sending the percentage given from the target tracking algorithm.
To make use of the video feed coming from the camera, we input the images into the YOLO V3 neural network to perform object detection. The neural network scans each image it receives, returning the position of each vehicle on the frame. We chose the YOLO V3 network because of our need for a program that can run at high speeds and its ability to detect 80 objects, which makes vehicle detection more accurate. Competing networks only offered slightly better accuracy for major decreases in speed. To increase our speeds even further, we decreased the network's data size from 32 bits to 8 bits. This allowed us to run multiple instructions at a time in the CPU and only resulted in very minor accuracy reduction. Moving on from object detection, the user selects a vehicle to begin the tracking process. To assist us with our target tracking, we made use of OpenCV, a computer vision library. Target tracking differs from object detection in that it searches for a predetermined set of pixels rather than assessing the entire frame for objects. We use the neural network object outputs to initialize the tracker. When vehicles were lost by the tracking algorithm, we continued to use the prediction to stay as close to the target as possible for quick acquisition upon relocking the target. If vehicles remain lost for multiple frames, we switch back to the neural network to make use of the greater accuracy. The vehicle closest to the target's predicted location is automatically chosen to reinitialize the tracking algorithm. This improves the robustness of our system and allows us to track in more cluttered environments. While target is being successfully tracked, motion commands are sent to our pan control system and the laser to keep it on target. To interface with the motion control, we used our motor's Python API, PyTrinamics, and to continue processing images while we're sending commands, we used multi-threading to run them simultaneously. Coding for the project was done in Python.
At first, we accomplished the detection of potential targets in a clouded background. This was done using a neural network. Once the detection and tracking at 50 meters were done, we encountered problems detecting objects at the larger distances. To overcome this roadblock, we incorporated a zoom function, which increased the resolution that the neural network sees when trying to detect objects. As we can see in this video, the zoom portion is pasted back to the original frame. Another issue that we ran into was that the laser went off of our target as we approached the edges of our field of view. To solve that, we increased the range of motion of our motion control algorithm to perfectly align with the field of view.
Despite the tracking algorithm running faster than our requirements dictated, we found it hard for our motion control to keep up with objects moving at high speeds. To account for this, we incorporated the vehicle's velocity into the motion algorithm. This way we could predict the location of a vehicle based on previous movement.
In this video, we can see that our system tracks the target at twice the requirement speed.
We use test, analysis, and inspection to verify all of our requirements, and as you can see here, all of our verifications were successful.
Those are the deliverables that have been submitted throughout the 2 semesters, all verified by the mentor and the sponsor. Deliverables have their formats and their due dates on the table below.
As mentioned before, the requirements for our product were to track a white van going at a constant speed of 28 kilometers per hour or 17 miles per hour at a distance of 50 to 300 meters traveling orthogonal to the tracking system. We created a robust product that exceeded the requirements of the project. First of all, we can see that our system performs successful tracking at distances of 50 and 100 meters, which is the longest range we had available. However, we did prove that our system can detect a target from 300 meters away, and according to our hypotheses and testing, we believe they will be easier to track a target at longer distances. We also were able to track in daytime, dusk, and dawn. Secondly, we demonstrated tracking of a Toyota Avalon, which is a much smaller target than a white van. And lastly, we can see that our system performs successful tracking even when the car changes speeds and directions. In addition to that, the maximum speed we tracked the car was 33 miles per hour, which is almost twice of our requirement.